The set of all linear combinations of vectors v1 through vn is called the span of those vectors. It's written this way. Let's go back to the challenge response system. So Eve knows the password satisfies a bunch of equations. She can calculate the response to any challenge that lies in the span of the vectors a1 through am. Here's how. So any vector in the span can be represented as a linear combination of the vectors a1 through am. Now we use the distributive law. The dot product of a with the password x by the distributive law is the sum of the dot products of these vectors. Now we use another algebraic property to move the alphas out. And Eve knows these dot products because she's observed the challenge and the response. So she plugs in the responses to those challenges, and she can get the response to A. So this shows that she can compute the response to any challenge that lies in the span of A1 through AM. Are there any other challenges for which you can derive the response? The answer to that question will have to wait. Let big V be a set of vectors. If V1 through Vn are vectors such that big V equals span of V1 through Vn, we say that V1 through Vn form a generating set for big V. We refer to these as generators. Here's an example. I claim that these vectors are a generating set for R3. So why is that? We have to show two things. First, that every linear combination of these vectors lies in R3. And every vector in R3 is some linear combination of these three vectors. The first statement is pretty easy. Each of these vectors is in R3. You multiply them by scalars, they're still in R3. You add them together, still in R3. What about the second statement? We prove this as follows. Let x, y, z be any element of R3. And I want to show that I can express this vector as a linear combination of these three vectors. Well, here's a formula for that. The vector x, y, z can be expressed as x over 3 times the first vector plus y over 2 times the second vector plus z times the third vector. Now, I claim that this is another generating set for R3. Now, another way of showing that every vector in R3 is in the span of these vectors is this. We already know that R3 is equal to the span of these old vectors. What I'm going to do is show that each of these old vectors is in the span of the new vectors. I do that by exhibiting a linear combination. The first vector is 3 times the old vector. The second vector is minus 2 times the first old vector plus 2 times the second old vector, and so on. So I've shown that the new vectors are in the span of the old vectors. Now, why does that do the job? Well, we already know that any vector in R3 can be written as a linear combination of the old vectors. And we know that each of the old vectors can be written as a linear combination of the new vectors. To put these together, we use the fact that a linear combination of linear combinations can be reduced to just a linear combination. Let's see how that goes. So we write x, y, z as a linear combination of the old vectors. Then we replace each of the old vectors with an equivalent linear combination. So we're just substituting from the equations on the previous slide. Now we multiply through using our algebraic properties, and then we collect like terms. And we end up with a linear combination in terms of the new vectors. Now, writing the vector x, y, z as a linear combination of these vectors was easy because these have a special form. it's even easier if we have a slightly more special form, if we use the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, because then the linear combination looks like this. X, Y, Z is x times the first vector plus y times the second vector plus z times the third vector. We call these standard generators for R3. And they're traditionally written E1, E2, and E3. Here's a way we can use standard generators. Consider the question, can 2 by 2 lights out be solved regardless of the starting position? What we're asking is whether the 2 by 2 button vectors are generators for the set of all initial states. The answer is yes. And here's how we prove it. We show that each of the standard generators can be written as a linear combination of the button vectors. So these are the standard vectors for 2 by 2 lights out, and we've written each of them as a linear combination of the button vectors. We already know that the set of all states is the span of the standard generators. And now we've shown each of the standard generators in turn can be written in terms of the button vectors. It follows that each of the possible states for 2 by 2 lights out can be written as a linear combination of the button vectors.